All right, as we begin a new topic, I want us to notice that this is among the first times this semester we have delved into the E word. The E word, of course, being energy. Now, we did make mention of the fact that chemical bonds store different amounts of energy, or that it takes different amounts of energy to disrupt chemical bonds. As a matter of fact, that is the main focus of what we are going to do in this particular part of the unit of study. That will be to look at how energy manifests itself, and generally what we mean by energy, and how chemistry contributes to energy. One thing you should recognize right off the bat is that you can probably claim that the reason that humans endeavored into harvesting and energy was when we were doing chemical processes to get chemistry from them. In particular, the most obvious case of that would be burning a fire. That was probably the earliest source of harvested energy for humans. And of course, later on, we added many other important sources of energy, in particular, energy derived from electricity became very, very important as well for humans. So let's just begin with some basic definitions of what we mean by energy. Then we will look at how chemistry has been an integral part of the science and activity of humans harvesting energy for the past several, if not the past couple thousand years. So energy we will define in a really kind of a nebulous way. Energy we will define as the ability to do work or supply heat. And what we will see coming up is that these are what we desire. This is what we desire energy to do for us. We desire to keep us warm, or to keep us at some stable temperature above what the ambient surroundings are supplying for us, or it is energy is going to be our ability to push or pull things around the room, to carry an object, or even such mundane processes, not really mundane, but important processes as beating our hearts and sucking air into and pushing air out of our lungs. So we will use energy, of course, to maintain some certain body temperature, to keep us alive, and we will also use energy to push nutrients around our body and suck nutrients out of the atmosphere in order to perform metabolic processes. Okay, so what we're going to do with energy is classify it into one or two forms. And the first is what we call the kinetic energy. That's what we want. That's our ability, as we will see, to do work or supply heat. And in a simple definition of what kinetic energy boils down to being, we will just draw from the word kinetic, which is part of the name of this. Kinetic means move it, kinesi or whatever, kinesiology, whatever you want to say, means motion. So kinetic energy is energy of motion, quite simply. This is the form of energy we desire. The second classification we will place to energy is what we will call potential energy. And what we can think of potential energy as manifesting itself as is in one of two ways. It's energy based on your position, or the position of objects relative to one another. And in another sense, we can think of potential energy as some stored form of kinetic energy, or a stored form which can be converted into kinetic energy. So as we say at the bottom, potential energy is the form we use to generate kinetic energy. So we will often take some supply of energy, maybe from some food we ingest, maybe from plugging something into the wall, maybe from the light of the sun, and we will convert that into the things we desire, those being heat and work that make us possible to be alive, or to simplify the lives that we lead. Let's look at several different classifications of these energy forms. I'm sure they're familiar to us. For potential energy, or the stored form of energy, the energy of position, we will have that expressed in what we call electromagnetic or light energy. It can be expressed as electrical energy, stuff we get out of the wall. It can be expressed as gravitational energy, like putting a large rock on a pulley and then letting the pulley fall to the earth to generate motion. It can be in the form of the nucleons stuck together in the nucleus of an atom, or what we will call nuclear energy. And it can be in chemical energy. Now, let's differentiate what we mean between 4 and 5. 4 and 5 are nuclear energy for the protons and neutrons shoved into the nucleus exclusively. And when I speak of number 5, the idea of chemical energy will be due to the connections between nuclei when they are combined together in compounds and molecules. And generally, the chemical energy is manifested in the way electrons are distributed between the connected nuclei. So we will pretty much generally think of it as such, that chemical energy is generated due to the electrons. Nuclear energy is generated due to the protons and the neutrons. Now, we are not going to worry about ripping nuclei apart in this particular class. What we're going to do almost invariably here is generate our energy from chemical processes. So when we rip bonds apart, it takes energy to break bonds apart, but there's also energy stored in bonds, and we can harvest the energy stored in bonds then and convert, as we said, this potential energy form into a form of motion which we desire to make our lives more simpler, or work better, or actually maintain our life. One of those two things we might do from that energy we get from the stored in chemical bonds. Okay, now let's move to the classifications of the kinetic form of energy. And they're very simple, and they are really part of the definition of what energy is. These are the forms of energy we really desire. We desire to get from energy mechanical work. So mechanical energy is what we mean by moving objects around, either me moving my arm up and down or a bulldozer lifting a pile of earth. That would all be classified as the energy of motion we call mechanical energy. Physicists would call this mechanical energy work. Or the other form, or the other type of this kinetic form of energy would be heat energy. Now, as we go a little further on, we'll be able to differentiate the distinct difference between heat and work energy, but right now, they're both forms of energy of motion, and right now, these are the desired forms of energy, and of course, we harvest these desired forms from the 5 forms above, and in particular, what we're going to be investigating in this section of study is how we can harvest energy from chemical bonds and use it to generate the energy of motion that we ultimately desire. First, give some general definitions that we will use throughout our discussion here of energy in chemistry. We will have what we call an open system. An open system is a system which will not allow matter in or out. A very simple example of an open system would be a beaker sitting on a laboratory bench that is not covered, and this allows exchange of matter between the liquid that is present in the vapor and the surrounding atmosphere in connection to the beaker. So that's what we mean by an open system. Open systems are dealing with matter exchange between two partitions in the universe in which we live. Now, the opposite to that would be a closed system. Closed system is a system that does not allow matter in or out. If you think about what would happen naturally if I let the beaker sit on the bench top long enough, the water will eventually evaporate out of the beaker. And if I come back sometime later, the beaker will be dry. But if I put a lid, like say I take a bottle of water and put the lid on the bottle of water and sit it on that tabletop, then that is closing the system, not allowing it to exchange matter with the external atmosphere, and I'm conserving matter in the system when I close the system. Okay, now let's talk about open and closed energetic systems, and they use fancier terms to describe them. First, we have what is known as an adiabatic system. Adiabatic is a fancy word, which means energy is not allowed in or out. And in particular, one of the ways in which we measure energy, there's several ways we can do it. We can do it with a voltmeter, yes, of course. We can do it with a light meter to see how bright light is that's shining on a system, yes, of course. But the simplest way and the longest standing way in which chemists have measured energy is with the good old thermometer. And of course, the thermometer is going to sense heat energy. And when we talk generally about an adiabatic system, it is generally meaning we're not going to allow heat in or out. Now, that does not necessarily limit the way the system is adiabatic. Of course, all energy is not allowed to flow in or out. But generally speaking, when we do things in laboratory, our easiest sensor and our longest standing sensor, which has been used for 300 years now in the science of chemistry, not quite, but getting close to it, that would be the thermometer, which would allow us to measure the heat energy content. Okay, then we will have a diathermic system, which means that you can exchange heat with a system and its surroundings. Dropping an ice cube into a glass of water creates a diathermic system. There's an exchange of heat between the two that we will describe later. I'd rather not get into the detail here, but that would be just one simple example. So anytime I let heat flow in or out, then that will be diathermic. Now, let's keep in mind that is just one type of energy which can be exchanged. We can also allow this to a diathermic motion system where I have transfer of motion from one body to another. The momentum of one imparts momentum into the other, so I can have transfer of energy of that form. I could also have diathermic systems which are transferring, say, electrical potential or things of that sort between one another, charge, which can be stored and separated out, can supply a form of potential energy that we can convert to run a fan or heat a stove coil or something of that type. So technically speaking, this diathermic system, even though the word thermic is in there, which implies something to do with heat, and generally speaking, that's pretty much the only form of energy we're going to investigate at this particular juncture. But however, you should keep in mind that generally, not only am talking about allowing heat to be exchanged in or out of a system, I could be allowing motion to be exchanged, I could be allowing electrical charge or energy stored to be exchanged, any of the other forms as well. Now, when you isolate a system, that means you close it off and make it adiabatic. You don't let matter or energy in or out. Now, again, I was very explicit with my isolated system here. We could talk about energy or we could talk about heat. Generally, again, we will speak almost exclusively about heat being allowed in or out as our form of energy. Now, then let's define what we call thermodynamics. That is the study of energy flow between objects. And we have what we know as the first law of thermodynamics. That is that our universe is an isolated system. And an isolated system means it's closed and adiabatic. And it means that there is no energy allowed in or out of our universe. And what it's saying is that energy is conserved in our universe and is only interconverted between various forms. As we attempt to measure energy, we know energy must have some measurable units to be described in. There are several different ways in which energy can be described. Several different units have been used in antiquity and in modern days as well. We will go, of course, with the SI unit of energy. The SI unit of energy is named in honor of James Prescott Joule, who early in the 1800s did some pioneering work on measuring the interconversion of mechanical energy into heat energy, proving that there could be a conversion of this type of energy, which was before that they were thought to be completely different entities. Maybe we'll have some description of some of those ideas later on, but he did the first really careful measurements showing that forms of energy could be interconverted into one another. In particular, heat could be could be converted into heat, measurable temperature change. And the Joule unit of energy is defined then as a derived unit. Remember, we talked about that at some time earlier. It is a combination of other base SI units. And you'll note that a joule is a kilogram times a meter squared divided by a second squared. Now that might seem really difficult to keep track of those weird combination of derived units, but I would offer to you that this is a very important one and you probably should know it, but also that you can think a little bit from a simple relationship that is very familiar to us, what might be the quantities that go into this. And that simple relationship would be that the kinetic energy a moving object has, it can be calculated by the formula that kinetic energy is 1/2 mv squared, where m is the mass of the object and v is the velocity of the object, and you will square that velocity. So if you look at these units, mv squared would be m is measured in kilograms, the mass of the object, and the velocity is the displacement of the object measured in meters per second, and you square that. So the units of energy are going to be kilogram meter squared per second squared. Now I am describing this energy unit in terms of the kinetic energy of motion, and that might seem to be completely different than maybe what energy units we should use for heat, or energy units for electricity, or gravity, or light, or what's stored in a nucleus, or in a chemical bond. But you should keep in mind that all forms of energy can be interconverted between one another, and that they can all be expressed in these same units of joules. So please keep that in mind when you're thinking that I can express any of the quantities I showed 2 slides back. Any of them can be expressed and measured in these SI units of joules. Give you some general ideas about the magnitude of the joule unit of energy. First of all, I will point out to you that the joule unit, this kilogram meter squared per second squared, turns out to be a very tiny amount of energy. And so what we do is we scale it very frequently into kilojoules or megajoules, or we use alternative units, which happen to be a little bit bigger to measure some of our normal energy values in nature. We'll get into some of those later. So let's just take a look at some various values of energy that occur when we are doing everyday things. The energy required to sleep for 1 hour is a value of 10 to the 5th joules. Now that is 100,000 joules. Now, in case you think that that's a lot of energy, in the relative scheme of things, I mean, in order, of course, for your heart to pump and your lungs to pull air in and out and all these things, it does take energy to do these things, and these actions must be sustained to keep you alive while you're sleeping. But I don't think anybody believes that there's a huge amount of energy being expended while you sleep. So this gives you some basic idea about how much energy or how big the unit of energy known as the joule happens to be. Well, just for connection with another familiar unit, if we divide this number by 4,000, we would get the energy that it takes to express this in food calories. So if I do that, divide this by 4,000, I will get something like 20. So you are expending 20 calories of energy as you sleep for 1 hour. And that seems a little more realistic to us. Then when we see a little bit further up there, the energy that is present in a donut or a little bit of pasta or something like that, I think the donut must not have much sugar or sprinkles on it or anything like that, because that's saying that that's about 200 calories. It's 1,000,000 of these joule units, or about 200 of these things that we normally associate with energy in our food content of calories. Now, as we go up this scale, we note that a gallon of gas has 100 million joules or 100 megajoules of energy in it. We note that the energy used per person in the US is almost a trillion. Remember, a billion would be 10 to the 9. So this would be 1/10 of a trillion of joules of energy used by each person. Then you will note how much energy reaches us from the sun that hits the earth. And that's a wealth of energy coming from the sun, which of course through a series of processes can be converted into by plants into the growth of the plants and stored in the plants. And the plants can be eaten by the animals, and the animals can be eaten by the humans, or we can even eat the plants for that matter. And so we can get the conversion of the sun's energy through this mechanism and harvest energy directly from the sun. Now, of course, not all the energy from the sun is directly converted into plant energy or chemical bond energy. A lot of it is just reflected back into space, and a lot of it is not being harvested by us, but we could certainly take better advantage of the source of the sun, and that's probably our most likely viable source of energy that is sustainable and safe, that we can take further advantage of over the next millennia as we exhaust our more familiar fossil fuels. You'll notice that the energy consumption in the US in 1 year, 10 to the 20 joules, that's a ridiculously big number. It's really out of proportion for the size and population of the United States compared to the rest of the world. But then when you look at the world's reserves of fossil fuel, how much energy is in the fossil fuel reserve. It's only 1,000 times more than what we use in this country every year. That's really not a sustainable plan. Of course, these numbers are a little old now, even, and that number for the world reserves has probably gone down pretty substantially. So we need, of course, to explore alternative energy sources if we want our grandchildren and great-grandchildren to experience the kinds of existences that we have taken advantage of on this planet. Okay, now another thing I want to say, you shouldn't expect that I would ask you to memorize any of these numbers. These are just numbers that are giving us some perspective of the size and scale of the joule unit and the relative amount of energy that might be consumed during various processes. Let's remind ourselves about these concepts again. Let's accumulate them all together again. First of all, we're going to be focusing on what is commonly referred to as thermochemistry. And that sounds like the heat derived in chemistry, and in a way it is, because for quite some time now, we have used and relied upon the thermometer to measure the energy evolving in chemical or being supplied to carry out chemical reactions. So in that regard, we can sense energetic change in chemistry by sensing a change in temperature that the system undergoes. So this is very commonly referred to as thermochemistry, but in general, this will be the energetics of chemical processes as they occur, whether you have to input or whether energy is expelled during them. Now, in general, we should keep in mind that we are going to focus on chemical energy being converted into other forms. Like when you burn a fire, you're generating sound energy, you're generating heat energy, you're generating light energy. So all these forms of energy can be thought of as a result of the motion of the particles and their movement. But in general, all kinds of energy can be converted into other forms. I talked earlier about the fact that light and heat or energy from the sun is converted in the plants into chemical bond energy, which is later chewed up by animals and converted into mechanical energy. So there's just a transfer of the forms of energy around and around and around. Now, really, we should keep in mind energy is not allowed into or out of our universe. There's a conservation of energy in the universe. It's what is here is here. It's not going anywhere. We're just constantly converting it from one form into another. The energy content of the universe is fixed, and it's not being created. It's not being destroyed. But in fact, what was discovered by Einstein about 100 years ago is that we could interconvert matter and energy if we so desire. Generally speaking, the processes we carry out are not going to do such bizarre things as convert matter into energy. They're just going to release the potential energy stored in chemical bonds in various processes. Let's now compare and contrast the forms of kinetic energy which we desire, and those are the heat and work we can get from stored forms of energy, and in particular, the stored forms of energy we're going to get our heat and work from are the potential energy locked up in the bonding relationships between connected nuclei. So chemical bonds are going to be broken, and we're going to harvest the potential energy stored in the chemical bonds, and we are going to convert that into the heat and work we desire. So heat and work are both motion. So if we went down to the nanoscopic level, we should be able to differentiate motion generated in the form of heat compared to motion generated in the form of work. And quite simply, heat at the nanoscopic level is motion, and it's the matter that possesses that heat energy in motion, but the way the motion manifests itself is that it is random. And when I say that it is random, I mean that it is completely random, meaning if I dump heat energy into a sample of matter, the more heat energy I dump in, the more dramatically the matter moves. And if I put a thermometer on to that matter, I would note that the temperature of the matter is rising as I input more heat energy into it. Really what is going on, if we want to get down to what is actually occurring, the matter in motion bumps into the thermometer, which bumps into the glass, which forces the glass to move more dramatically, which transfers to the liquid in the thermometer, forcing it to move more dramatically, and then this liquid expands naturally as the molecules in the liquid are heated. So we use this to measure temperature, the scale to which, we scale how much expansion the liquid undergoes as it moves more dramatically, and it tells us something about the temperature that it contains, and therefore the amount of heat energy it possessed. Now, this heat energy is motion that is completely random, meaning if I have 100 atoms in the sample, then there's one moving straight up, simultaneously there's one moving straight down, simultaneously there's one moving to the left, there's one to the right, there's one at a diagonal of 20 degrees, there's one at a diagonal of 270 degrees, and on it goes. Every angle and direction of motion is equally likely. So this is what we mean by this random form of motion. All directions exactly likely to occur so that there's a complete motion in all possible way. Now let's contrast that to the form of kinetic energy we called work. Work is what I will classify at the nanoscopic level as concerted molecular motion. And what I mean by concerted is now when I impart this motion into the matter, they all move in the same way. So when I push on a block, every atom in the block, it has a concerted direction of motion applied to it. Now the block also has a temperature, and that means the atoms are in motion due to the temperature that the block possesses. And if I stick a thermometer on touching the block, it'll transfer the motion into the liquid in the thermometer, causing the liquid in the thermometer to either expand or contract to a certain extent, which will tell me the temperature of the block. But the point would be that the heat energy content of the block means that all the atoms in the block are moving completely random to one another. For everyone moving upward, there's one moving down one. For everyone moving left, there's one moving right. For everyone moving diagonal in one way, there's one moving diagonal in the other sense. So now, again, though, if I push the block, every atom concertedly moves in the same direction. So heat and work are both motion. It's just a matter of whether the motion is concerted, then we will classify that as mechanical energy or work, or if the motion is randomized, and we will then call that type of motion the heat energy content of the system. Let's introduce a quantity that is going to help us sense the relationship between the temperature of an object and how much heat energy it contains, and that will be known as the heat capacity. The heat capacity is a quantity which says how much energy is present in the sample relative to the temperature we measure for that particular sample. So in a way, it measures a substance's ability to hide heat energy in it. Now, let's understand what I mean by the heat capacity of a material by thinking about a couple different materials that we could place sitting out in the sun. Let's suppose I have 3 park benches in the sun. One of them is a wooden bench, one of them is a metal bench, and one of them is a plastic bench. They're all the same distance from the sun. They're all being bombarded by the same amount of sunlight from the sun. However, if you touch them to sense their temperature, you would note dramatic differences in the materials, and based on the materials that the benches are made out of, they would each display different temperatures. If you put thermometers on them or if you put your hand on them, you would be able to tell that each of these substances came to a different temperature, even though it is being bathed by the same heat capacity from the surroundings. So the point would be that if the heat capacity of a material is high, then it will have a lower change in temperature as you add heat energy into it. So for substances with a big heat capacity, they experience small change in temperature with input heat. Substances with low heat capacity experience big temperature change with an amount of input heat. So what affects the heat capacity of a material? Well, quite simply, the amount of the material will impact its heat capacity. And this is quite obvious, say if you're trying to boil a small pot of water or a large pot of water. We all know that you're going to have to put way more heat energy into a large pot of water to bring the water up to a boil than you will putting heat energy into a small pot of water. The more matter you have, the more heat it takes to change the temperature. As a matter of fact, it scales directly proportionally. If you double the amount of matter, you will have to double the amount of heat energy you put into it to raise the temperature the same extent. Now, the second factor which is going to affect the heat capacity is, generally speaking, the makeup of the matter itself, how the matter is bonded, what types of bonds it's using, how far apart the atoms are, what angles the atoms are at, how strong the bonds are between the atoms. All these factors will help store heat energy within the substance and therefore have different manifestations of temperature change that the substance will undergo when heat is added or removed. So, in conclusion here, the higher the heat capacity, then the smaller the change in temperature you will experience with a given input amount of heat. Now, this works whether the heat is added or the heat is removed. If I remove heat energy, of course, the temperature is going to go down. If I add heat energy, the temperature is going to go up. But both of these factors are scaled by the heat capacity of the matter. If the material has a low heat capacity and I remove heat from it, its temperature will go down more dramatically than a material with high heat capacity. We have our magic formula, which relates the heat energy content, Q, to the heat capacity of the material, C, times the change in temperature the material undergoes, delta T. Now, delta T is always defined as the final temperature minus the initial temperature. So delta T can actually then have a sign, because if TF is less than TI, then delta T is negative. And we'll assume C is a positive heat capacity value, then Q is negative. And that means that heat energy can have a sign. The heat energy can be positive or negative. If the heat energy is negative, the temperature is going down in the system. Now what that means is when the temperature goes down, the heat energy is negative. We're going to call that exothermic. Heat is being removed from the system when the temperature goes down. Okay, now let's go the opposite way. What happens if we add energy? Q is going to, or delta T in that case is going to be positive because TF is greater than TI. Then if C is a positive number, Q will also be a positive number. So when we add energy, we will say Q is a positive number, and that is what we will call an endothermic process. So endothermic processes have positive Q, and a positive Q means they have a positive delta T, which means TF was bigger than TI. If we have an exothermic process, we have a negative Q. If we have a negative Q, we have a negative delta T. If we have a negative delta T, that means TF is less than TI. And the temperature is going down in an exothermic process. Now, another thing that we commonly do to express the dependence of the heat capacity on the amount of matter present is that we break C down into M times SH, or the mass of the object times the specific heat of the material. So C being M times SH means C can be expressed as the mass of material present times a new quantity specific heat, which tells us something about the bonding of the material. So the two factors which affect heat capacity are mass, or how much matter is present, and the bonding of the material, how it's put together. So the M value tells you how much matter is present. The SH value tells you how the matter is put together. So if we substitute for C that it is M times SH, then we have a simple expression for the heat energy content of a sample, or how the temperature changes in the sample with change in heat energy content. And that would be that Q is equal to M times SH times delta T for that material. So we have our working formula to relate the heat added to a substance to how much temperature change it will undergo. That is Q equals the mass of the substance times the specific heat of the substance times delta T. Now, if we were to solve that equation for the specific heat, we would note that SH is equal to Q divided by M divided by delta T, and knowing the units of those quantities, we could decide that the units of specific heat must be joule per gram per degree C. If we're going to measure the heat supplied to the substance in joules, if we're going to measure the mass of the substance in the sample in grams, and we're going to measure the change in temperature that the substance undergoes in degrees Celsius, then the units of specific heat will be joule divided by gram divided by degrees C. And what I list below that formula is the specific heat of some substances. Now, of course, as you can imagine, scientists have studied this property very thoroughly, and you can pretty much find a specific heat value for any material that you like, whether it's a solid, whether it's a liquid, or whether it's a gas. One thing you should note is that the metals in general have a relatively small number representing their specific heat. Like, for instance, let's just take, for example, iron has a specific heat of 0.450 joule per gram per degree C, while aluminum has a specific heat of 0.897 joule per gram per degree C. Now, here's the implication of that. The number for the specific heat of aluminum is essentially twice the number for the specific heat of iron. What that means is if you weigh out the same amount of iron and aluminum, the temperature change that the iron would undergo is twice as much change in temperature as the aluminum would undergo. Why? Because the heat capacity of aluminum is twice as much as the heat capacity of iron, or more directly the specific heat is. But if you use the same mass of each, those difference in the size of those numbers say that the temperature change for an equivalent amount of heat would be twice as much temperature change in the iron as you would see temperature change in aluminum. Now you'll notice silver has about half the specific heat of iron. So that means that if you put the same amount of heat into the same amount of iron and silver, that the silver would change temperature twice as much as the iron. Now remember, for the aluminum, if you compared the same amount of those, the silver would change temperature 4 times as much as the amount of aluminum would change, because the specific heat of silver is about 1/4 the specific heat of what you see for aluminum. Now, one more thing I want to point out here is that I would not expect you to know these specific heat values. If you were asked to use one in our upcoming final exam, I would supply that value for you on the test. And lastly, what I would like to point out is that you should note the specific heat of liquid water. The specific heat of liquid water is massive compared to the specific heat of these other materials. Compare it to the specific heat of iron. The specific heat of liquid water is almost 10 times the specific heat of iron. What does that mean? If you take equal masses of water and iron and put the same amount of heat into them, the iron will change temperature 10 times as much as the water will change temperature. Water, and in particular liquid water, has an amazingly big specific heat, one of the biggest specific heats in nature. And this is a very important property for the planet Earth. Remember, the Earth contains a massive amount of water, contrasted to the Moon, which has no water. Now, the Earth and Moon are essentially the same distance from the Sun, and essentially they are bombarded by the same amount of heat energy from the Sun. But because the Earth is covered with such a huge amount of liquid water, and this liquid water has a huge heat capacity, the change in temperature that the Earth undergoes from day to night is 20, 30, maybe 40 degrees C. Is a dramatic, that is, believe me, a very dramatic, I would say more likely 20 to 30 degrees C. I'm not talking Fahrenheit, I'm talking degrees C. 25 degrees C would be a fairly dramatic change in Celsius temperature from day to night, but on the Moon, the change in Celsius temperature from day to night is probably 400 degrees C. Now, the ramifications of such a dramatic swing in the change in temperature on developing life systems would be cataclysmic. So one of the factors, besides so many others, that makes the Earth a fertile ground for the development of life is the stability of the temperature from day to night on the Earth, due to the fact that there's such a large amount of water on the Earth to help regulate the temperature on the Earth. So that is a very important factor as to how the Earth was able to develop and sustain life. Look at an example of using the specific heat formula, you can go to my calorimetry help page and do a bunch of practice problems of this type in preparation for your final exam. So how many joules of energy must be added to 125 grams of iron to raise its temperature from 22 to 215 degrees C? To do a problem like this, you would have to know the specific heat of iron, which I would supply for you as being 0.450 joule per gram per degree C. You can calculate delta T as the change in temperature. You always do this as the final minus the initial. So I'm going from 22 to 215. So TF is 215. TI is 22. I subtract them and I get a positive 193, which is very important that I note the sign of delta T, because when I put in a positive M of 125 grams, put it in a positive SH of 0.450 joule per gram per degree C, the positive delta T is going to give me a positive Q value. So when I multiply all the values together, check the dimensionality of the problem, I get that Q is 10,900 joules. Now notice I am also converting that to a more reasonable sized number that eliminates the significant problem of the zeros that I have in 10,900 joules. Since a kilojoule is a 1,000 joules, just like a kilometer is 1,000 meters, I can convert my joules to kilojoules by dividing by 1,000, and I find that Q is plus 10.9 kilojoules. Equally important, I find Q is a positive value, meaning I have to input, for positive Q, input 10.9 kilojoules in an endothermic process to raise the temperature of 125 grams of iron from 22 to 215 degrees C. Here's a second specific heat and calorimetry calculation example. So I'm asking here, how much heat must I remove from 220 grams of water to cool the water from 87 to 10? Now again, I would need the specific heat of liquid water, which is 4.184 joule per gram per degree C. Again, I would give you a value like that. Now what is important to you is that you note what the final and initial temperatures are and put them in the formula correctly. So the delta T is a negative 77 degrees C when I do this. So now I just put in the mass and the specific heat, cancel out some units, and when I do so, I get that Q is minus 70,900 joules, which of course I really don't like the size of that number. Put it into a little better unit by dividing by 1,000 and converting the joules to kilojoules. So this is negative 70.9 kilojoules, which is saying it is an exothermic process, which is saying I must remove 70.9 kilojoules of heat from 220 grams of water if I want to cool that water from 87 down to 10 degrees C. So the negative Q is telling me this is exothermic. In this example, I'm asked to find the final temperature of a piece of silver that weighs 515 grams, and I'm going to add 8.75 kilojoules of heat to the silver. Okay, now what I want you to recognize is because the specific heat of silver, which I would give you, of a value of 0.235 joule per gram per degree C, but most importantly, because it is in joule units, then the heat energy I add to this must also be expressed in joule units. So my 8.75 kilojoules of heat, I'm converting into joules, and by multiplying by 1,000, I find that's 8,750 joules. Because the process is endothermic, or because I am adding 8.75 kilojoules of heat, that means the 8,750 joules are positive when placed in the formula. So I rearrange my specific heat expression to solve for delta T, so that it is Q divided by M divided by SH. Plug in the values with a positive Q in joules, so that the joule unit of the specific heat cancels. Notice I get a cancellation of the gram units as well, and I get 1 over degrees C, which tells me the answer is in degrees C, and I'm getting a positive 72.3 degrees C. Now this is not TF. What the formula calculates for me is delta T. From the definition of delta T being TF minus TI, I can rearrange and get the TF is equal to delta T plus TI. And from the given TI of 12.0 degrees C, I get the TF must be 84.3 degrees C. One final example where I am now taking a piece of gold, a rather sizable chunk of gold, and I'm going to remove 25 kilojoules of heat. So I would first need to know the specific heat of gold, and notice that it is being expressed in joule per gram per degree C, and I was given my heat removed in kilojoules, so I have to convert my kilojoules to joules by multiplying by 1,000. Also, since the problem says I am removing the heat, removed heat is a negative Q. And the Q was not given to me as negative, but the statement of the problem tells me it must be negative. So I need to put a minus in front of my 25 kilojoules because the heat is being removed. It is exothermic. So when I convert that into joules, that's minus 25,000 joules. Then I rearrange the formula, solve for delta T, plug in my Q, mass, and SH values, and I get a change in temperature of negative 111 degrees C. Now that should make sense. If I'm removing heat, the temperature should go down. If I'm adding heat, the temperature should go up. Now this negative 111 does not reflect the final temperature of the gold. That is the change in temperature of the gold, and delta T is TF minus TI. So when I rearrange that, TF is delta T plus TI, and that will be equal to negative 26 degrees C. Let's look at the interesting problem of the equilibrium temperature that two objects come to if they are isolated from the surroundings, or insulated, if you like, from the surroundings, and are placed so that they can exchange heat energy between them. So let's suppose I have a hot object at a temperature of 125 degrees C, and that object is 125 grams of aluminum. I have a cooler object at 19 degrees C, which is 85 grams of iron, and I will need to know the specific heat of both of these, which again would be given to you. And let's suppose I insulate them. I put them in a cooler so that they can exchange heat between each other, but not with the surroundings. So this is an isolated system. And anytime you have an isolated system, no heat is allowed in or out. Okay, so the heat energy in here is not escaping to the air on the outside, and the air on the outside is not heating or cooling the objects in the interior. So Q of the system is 0. That might seem a little bit weird, but this is saying there's no exchange of heat between this insulated object and the outside world. Now the system is composed of a section of aluminum and a section of Fe. And Q of the system is 0. That equals Q of the aluminum plus Q of the Fe. If I solve that problem, what I find and learn is that Q of Al equals minus Q of Fe. This is a very important result of the first law of thermodynamics. Anytime objects exchange energy in the universe, it is just swapped between them so that one is gaining and one is losing. The hotter object obviously will cool off. The colder object obviously will warm up. So one of the objects is undergoing an endothermic process. The other object is undergoing an exothermic process. So one of them has the opposite sign of the other. Now, do I really care which side of this equation you give the minus sign to? No. I could have said minus QAL equals plus QFE. All the sign is saying is that there is a difference in transfer between these objects. One is giving, one is taking. One is exothermic, one is endothermic. One is the opposite sign of the other, but the magnitude of change is equal. None of the heat energy lost by the hot object is going to the external world. All of it is going to the other one. So as the aluminum cools, its temperature will drop, but simultaneously the iron will gain and its temperature will go up. So our job will be to find what is the final temperature that the system comes to. One of the good things we understand about the nature of the way the world works is that if they are isolated, they will come to the same final temperature. Now, if they were connected to the outside world, they would come to the same final temperature as the outside world. So if I put this system in the room and not insulate it, they eventually would both come to room temperature, even if one of them had to warm up to room temperature while the other one cooled off to room temperature. They eventually will equilibrate at the temperature of the room because ultimately they're exchanging energy with the room to come to that temperature. Well, here, since they're isolated, they will both come to some final temperature that is not necessarily the temperature of the room, but probably isn't the temperature of the room. But one thing is for sure, as they exchange heat between each other, they will thermally equilibrate with one another and come to the same final temperature. To find the thermal equilibrium temperature of the two objects, we must solve the equation Q of aluminum is minus Q of iron. So we substitute the formulas for Q, and we have MAl SHAL delta TAL is equal to minus MFE SHFE delta TFE. Now again, the minus sign, it does not matter which side of the equation it is on. It is only indicating that whatever change the left is undergoing, the right is undergoing the opposite change. So I just take the data from the previous slide, put the mass, the specific heats, and the initial temperatures for the iron and the aluminum into the formula, and I have unknown final temperatures. But since the system comes to thermal equilibrium, TF is the same for both. So now what I do, and you have to be a little careful and make sure you are a little careful with distributing the quantities. I have to take 125 times 0.902, then multiply that times TF minus 125. So be careful with your distribution of the numbers there on the left. Same thing is true on the right. I take negative 85 times 0.49, and I multiply that times TF minus 19. So when you distribute the numbers in there, make sure you're careful to get the values I show in the middle of 112.75 TF minus 14,094 equals negative 38.17 TF plus 725. You should verify that you can come to those conclusions. Then I gather terms up in TF on one side and the numbers on the other, as you see. Then I divide both sides by TF, and I get a final temperature that the aluminum and iron come to of 98.2 degrees. Look at another example of a thermal equilibrium problem. Again, you should go to my help page and look at the calorimetry problems and practice. Again, that's www.sclu.edu/wparkinson/help. Then there are something called calorimetry exercises. You can look at the calorimetry exercises and you will see problems of these types. So if I have 150 grams of copper at 175 degrees C and dump into 275 grams of water at 20 degrees C, so what final temperature do they come to? So there's an exchange of energy. We're going to assume that this is insulated so that there's no loss of energy to the outside world. And there's a heat exchange between the water and the copper, so the Q water is minus Q copper. Whatever energy is lost by the copper is gained by the water. So I take the values of the specific heat, mass, and initial temperatures, put them into the expression with an unknown TF. Again, I multiply on the left 275 times 4.18. Then I distribute that answer into TF minus 20. Get the equation you see in the middle. And on the right, I take minus 150 times 0.385. Multiply that together, distribute it across TF minus 175. And I get the bottom on the values on the right that you see in the middle. Put the TFs on the left by moving adding plus 0.57.75 TF to both sides, then dividing both sides by TF, and I get a final temperature of 27.4 degrees when I dump the hot copper into the cool water. Let's introduce an alternative energy unit, one that's maybe a little more familiar to us from commercial applications. This is called the calorie. And the calorie has a very simple definition. The calorie is the amount of heat energy required to raise 1 gram of water 1 degree C. Or the calorie is the amount of temperature that would drop by 1 degree C if you removed 1 calorie of heat energy from 1 gram of water. So this scales proportional to how water changes energy. Now remember earlier I talked about the fact that water has a very high heat capacity, so water, as materials go, can store a lot of heat energy with only slight changes in temperature. This has led people for years to measure energy by how much temperature change water undergoes when heat is added or removed. Now, to compare this number to the specific heats we were talking about earlier, we would have said that 4.184 joules of heat is required to raise 1 gram of water by 1 degree C. This comes directly from comparing the specific heat of water. 1 joule of energy, we'll say it this way, 1 calorie of energy is equivalent to 4.184 joules of heat. So the calorie unit is about as 1/4, or it's about 1/4 bigger, if you like, than a joule unit, because a joule will go up 4 times as much. Something measured in joules goes up 4 times as much numerically as it would in calorie units. So calories are the amount of energy required to raise 1 gram of water 1 degree C. There's another unit that you might have heard of called the BTU, the so-called British thermal unit. It's kind of funny because they don't use it in Britain anymore. They only use it here. A BTU is the amount of energy required to raise 1 pound of water 1 degree F. So that's a BTU, raising 1 pound of water 1 degree F. Here I'm talking about a calorie, which raises 1 gram water 1 degree C. So this is often used in calorimetry, where we throw substances in water and watch how much temperature the change the water undergoes to learn about the specific heat of the material that we're throwing in water. Probably those of you that are in the 123 lab did a calorimetry experiment where you're throwing various materials into water and looking at how their temperature changes, and in particular how the temperature of the water changes as well, to learn information about the specific heat of those materials. The calorie is scalable. If I heat 1 gram of water 30 degrees C, I have to add 30 calories. Or if I want to cool 4 grams of water 20 degrees C, I'd have to remove 80 calories to do a process like that. Now, it turns out that your mom and them know the word calorie, but the calorie they're speaking of is a food calorie. And it turns out that even though they have the exact same name, they're really not the same unit. A food calorie is a kilocalorie of the scientific type. A food calorie is 1,000 of these calories. So, in other words, if you put in a food calorie of heat into water, you'd raise 1,000 grams of the water 1 degree C because of the nature of the size of a food calorie being a kilocalorie of this type of energy. Let's introduce a very important thermodynamic quantity that is the general way in which chemists and physicists, for that matter, talk more specifically about the heat energy content of a process. That is known as the word enthalpy. It's a fancy word that is typically given the symbol capital H. And the capital H has some reference to heat. And how do we define enthalpy? It is the heat under the conditions that the atmosphere pushing down upon this system undergoing some kind of change is supplying a constant pressure. So enthalpy measures how much heat is exchanged between a system and its surroundings when there's constant pressure being applied to the system. The reason for this is in many instances the system has to push on that atmosphere. If it's expanding or contracting, the atmosphere is either pushing down on it, or the system itself, the system is being pushed down on by air, or the system itself is pushing up against the atmosphere. This, of course, requires energy. So some of the heat energy that you might expect to be expressed as a temperature change actually will be lost in dealing with expanding the universe to allow something to change phase and evaporate, or something of that type, or for the surface of a liquid to move upward into the atmosphere. This costs energy. So then there won't be as much energy in the motion of the matter that remains to cause a liquid thermometer bulb to expand. So there'll be a different change in temperature that occurs because of the presence of this constant pressure on the system of interest. So in a way, what we can say is enthalpy takes care of the energy cost of dealing with the atmosphere that is constantly pushing on us. So we don't even worry about that, because you would never have that energy available to you because it is wasted on dealing with the atmosphere. Now, it turns out in nature that this enthalpy has some very important properties that make it to be a useful tool in numeric assessment. And the first is that enthalpy is what we call an extensive property. Something that is extensive scales with how much matter is present. So if you double the amount of matter, you will double its enthalpy. If you cut the amount of matter by 1/3, it will have 1/3, it will take an addition of 1/3 the amount of this energy to perform the same change in temperature or something of that type. So when we say enthalpy is extensive, it scales with how much stuff is present in the sample. Now this is not the only extensive example of quantities in nature. Mass is extensive. If you double the material, you double its mass. Volume is extensive. If you double the material, you double its volume. Okay, but other things in nature are not extensive. Like if I look in a room and I check out the, say, the temperature doesn't scale with the size of the room. The room has the same temperature in it. So if I take a small portion of the room, it will have a certain temperature, expand that to a little bigger section, even bigger section. All these sections of the same room are at the same temperature. So temperature is what we call an intensive. It doesn't scale with the size of the system. Pressure is also an intensive. In a room, a little section of the room has a certain air pressure. In that section, if I now double the size of that section where I'm measuring the air pressure, it will be the same. If I triple the size of the area in that room, it'll be the same. So temperature is also an intensive property. The second equally important aspect of enthalpy and its behavior is that enthalpy is a so-called state function. Now, what it means to be a state function is that all you need to know is where you start and where you stop, and the change in enthalpy is equal to the starting point subtracted away from the stopping point. So delta H is HF minus HI, independent of how you get between HF and HI. You don't have to monitor the individual steps in between. On the individual steps in between, I'll be adding heat energy, removing, adding, removing, removing, adding, removing, over and over and over again. It doesn't matter. The total change in enthalpy will just be where I stop, subtracted from where I started. Other things exhibit the same type of property, like temperature. And that's why this does as well. If I heat and cool and heat and cool and heat and cool a thing 100 times, it doesn't matter what and how much I did on the individual steps of heating and cooling. All I need to know is where I started, and I subtract that from where I stopped, and that is the ultimate change in temperature that the system has undergone. Even though individual steps might have been way lower than that change, way greater than that change, as long as I know them all accumulated together, I just need to know where I start and where I stop. Same thing is true with delta V. It is a state function. All I need to know is where I start and where I stop. It doesn't matter if I add, remove, add, remove, add, remove a million times during the course of the process. Delta V is only VF minus VI, independent of how I get between VF and VI.